Welcome back to Chapter 10, Part 2 on muscles. We are on video number 3, and in this video, we're going to be talking about a couple of diagrams that relate to muscle contraction. So in the previous video, we talked about what a muscle twitch looks like with respect to tension and time. So it's a single contraction of all the muscle fibers in a motor unit. So right here is a stimulus frequency, which is added onto this chart. And here we have two different muscle action potentials. So we end up going through the lag phase. We have the contraction and relaxation, and then we are hit with another muscle action potential. So we end up with the same thing. So muscle twitches are basically the same size. But if we start getting them closer together, the muscle can't fully relax until we end up hitting it with another action potential, which causes the contraction tension to increase slightly. So in this diagram right here, the muscle cannot fully relax and tension builds up. So we can't relax all the cross bridges. Some of them are still attached. So we end up with the contraction occurring more. So the muscle sarcomeres cannot fully go back to the original position. They just start to overlap even more with each subsequent stimulation from an action potential. Now, if we start getting them even closer together, you can see how it kind of looks like Bart Simpson's head here. That we end up with very little relaxation, and then we end up staying up in this range. So in this one, there is very little relaxation, and we end up with something called incomplete tetanus. Tetanus means constant muscle contraction, but this is incomplete. Here we are getting maximum stimulation. So this is as fast as the action potentials can occur. There is no relaxation of the muscle. So we end up with a constant contraction. Due to maximum stimulation. So this word tetanus means constant contraction. And this is complete. So this is due to the absolute refractory period of nerve action potentials, giving us the maximum frequency of stimulation. So the muscle stays contracted for however long those action potentials are being generated at maximum frequency. So the next diagram looks like this. This again is going to be tension versus time. And up here is where we reach a maximum. This looks like it almost like an incomplete tetanus right here. So we've zoomed in on that Bart Simpson's head part, but you can see that right here, if we look, these values generate a little bit higher until we reach a maximum, and it remains the same across the top. This is a phenomenon called trepa or trepe. I've heard it pronounced both. It literally means staircase. So it looks like a set of stairs. So you're going 1 stair, 2 stairs, 3 stairs, and then we're at the landing. This is a graded response. Graded means that it gets larger and has a slope. This occurs in muscle that has rested for a long period of time. So in this, it's a buildup of tension. Even though the stimulation is at maximum frequency. So a second stimulus generates a stronger contraction until the max is reached. Now, this is due to calcium levels. So we end up with a buildup of Ca+2 in the sarcoplasm. So only so much can be released from the sarcoplasmic reticulum, but it doesn't have a chance to get pumped back in because as soon as it gets pumped back in, it's released again. So it takes a little bit of time for all of the calcium to be released, or the majority of it. But this helps us because we can't go straight to maximum contraction. Those of you that participate in sports rely on this because if your muscles are not warmed up, you can actually injure your muscles. So a lot of times the first thing you do before you go out and practice or before a game is you do warm-ups, you do stretches. What you are doing is you are conditioning your muscles and you are going through this trepa. So warm-ups are a big part of any kind of sports or exercise. These allow trepa to occur, but they also help increase blood flow to the muscles. Because blood is going to be carrying the nutrients, the glucose, it's going to be carrying the oxygen. Also, contracting your muscles pushes on the blood vessels to get them to start flowing a little bit better too. So this all works in tandem. This also increases the temperature because we know that enzymes function better at body temperature, 96.8 degrees Fahrenheit or 37 degrees Celsius. So by increasing the temperature, we're making sure that those muscles are warmed up, hence the title warm-ups. And it helps all those enzymes like ATP, myosin ATPase, acetylcholinesterase, all of those things are working at maximum benefit, so we can end up with a maximum performance. So all of this stuff that you do that you might think, I don't need to warm up, I'm okay, it does have a basis in science.